I wanted to go over how I designed the generator. The equations I'm going to present are pretty specific for this style generator. The generator has one plate with round magnets all touching each other, and then a coil, and it's going to be a serpentine coil. So I think though that just looking at the equations you can adapt it to whatever generator you want. So anyhow, the first step is to have some specifications so that the generator is compatible with the wind turbine. And so we're going to start with our generator model, and it's going to be quite a simple one. I'm not going to get too sophisticated here. So I've got a generator that's producing an AC voltage, and this is going to be single phase. And then there's going to be a stator resistance, just a pure resistance, an ideal diode, and it's feeding a battery. And the battery is an ideal battery. There's no resistance in there, and I'm just going to keep it at a fixed voltage. So anyhow, VOC is the open circuit voltage, RS is the stator resistance, VBAT is the battery voltage. We're going to have some current going through there. And whenever the open circuit voltage is larger than the battery, we get a current. That's the difference of those two voltages divided by the stator resistance. Okay, if we want to talk about power, power consumed from the turbine, so there's shaft power going in here, and that's going to be this current times the open circuit voltage. And then there's power delivered to the battery, and that's going to be that current times the voltage of the battery. So we've got some shaft power coming in and electrical power going to the battery. And we just multiply it by the different voltages here. Okay, so I'm assuming that I'm going to have a sinusoidal waveform. That might not be true. Like if you had widely spaced magnets, you might just get voltage spikes. In this case, I don't think I'm going to get that. I think I'm going to get close to a sinusoidal waveform. And I'm just assuming it's full wave rectified, so it goes like this and then just repeats. So it goes for 180 degrees of the phase cycle and then just repeats. And if we plot voltage versus that phase angle, I'm modeling the open circuit voltage as some peak value, V peak, times the sine of this angle. So it follows the sine curve. And then the battery voltage is a constant, and we get power whenever this open circuit voltage is larger than the battery voltage. So right during this part of the cycle we get power produced or consumed, depending on how you want to look at it. So the power consumed from the turbine is the current. Again, it's open circuit voltage minus battery over stator resistance times the open circuit voltage. So at any point you can look at the difference in the voltage, find the current, and then multiply by that voltage. Power produced or delivered to the battery, that same current times the battery voltage. And note, this is instantaneous power, it's not RMS. So every point in time we have to calculate the power that's being produced or consumed. And then what we do is we take the average over that entire half cycle. And what I do is I do it numerically using a spreadsheet. Alright, so keep that in mind for the generator. Let's quick look at the wind turbine model here. We're just modeling power that's available from the wind. This is shaft power that the turbine is able to deliver. And 1/2 coefficient of performance times density of the air times the area of the turbine times the wind speed cubed. Okay, we're trying to keep our units consistent here. And near sea level, the density of air is around 1.2 kilograms per meter cubed. We're assuming that the turbine is spinning at about proportional to the wind itself. So you double the wind, you double the speed, and then we have something called a tip speed ratio. I'm just have it for lambda here. and it's the velocity of the tip of the wind turbine divided by the wind speed, or the free wind speed, not, you know, it's, so this tip velocity is going to be the radius of the turbine times its angular speed in radians per second divided by the wind speed. And we're assuming it's approximately constant. And if we assume that that's a constant, we can calculate this omega just by rearranging things based on the wind speed. Or what we'll be doing is converting it to RPM. So if we multiply by 30 over pi, then we express it in terms of RPM instead of radians per second. Then there's another term, cut-in speed, the wind speed at which the voltage is high enough to start charging the battery. And this is something we just specify for our design. And I'm saying at this cut-in speed, the peak voltage is equal to the battery voltage, and anything above that, and we start producing power. So this particular turbine, we've got a diameter of 0.4 meters, a height of 0.64 meters, so we've got an area of 0.256. I'm assuming a coefficient of performance of 0.2, tip speed ratio, I'm just saying is 1.08. I measured 1.2 approximately with it unloaded, and I just figured that loaded would be about 90% of that. Then I've got a cut-in wind speed of 2.8 meters per second. It just seemed like a good time to cut in at about 6.3 miles per hour. And I'm assuming a battery voltage of 14 volts. So if I plug in those values, I can calculate power in the wind, 0.03072. That's too many decimal places, but I'm just carrying them through. Times the speed of the wind cubed, and we can figure the turbine speed is 51.57 times the wind speed in RPM. And so if we say at 2.8 meters per second is our cut-in, then we've got a speed of 144 RPM at that wind speed of 2.8 meters per second. So this is the speed at which our generator has to reach 14 volts. Here's the spreadsheet I used to get the specifications for the generator. Just input various parameters here, battery voltage, cut-in speed, and wind turbine parameters here. The stator resistance is a number that I can adjust and see what the effect of the adjustment is. And so here I have a column with wind speed. I have it going from 2 meters per second to 8 meters per second. And then using that power equation for wind turbines, I can calculate wind power. This is shaft power available from the wind turbine based on the wind speed. And using tip speed ratio, I can calculate the expected rotational speed at these different wind speeds. So I've got the power available, I've got the speed of the turbine. Then we can look at the generator itself. Have a cut-in speed of 2.8 meters per second and a battery voltage of 14, so that's my anchor right there, and the voltage will vary linearly with the different speeds. So you can estimate what peak voltage you should see at different wind speeds. Right, and then the open circuit voltage, I'm assuming is following a sine wave, like for this half cycle here, going from 0 to 180 degrees. You get an open circuit voltage that looks like that. And to generate that, what I did was I made a row here with angles going 0 to 180 degrees and took the sine of that angle, and then I could multiply this peak voltage times the sine, so I could calculate the open circuit voltage for all these different speeds. So you kind of get a large table like that, but it's not too hard with a spreadsheet. So I can model the open circuit voltage, and then to calculate power, what I do is I have a conditional statement in here where I say if the open circuit voltage is greater than the battery voltage, then I calculate power using that, figuring the current and multiplying by the open circuit voltage. If it's less than the battery voltage, then the power is 0. So when the speed is low and the peak voltage is less than battery voltage, we just get 0 power. However, like here, we get a little bit above the battery voltage at some point, and we start producing power. And that's this red curve here. So this is just representative. And then at the very end here, what I do is I take the average of all those points for that half cycle there, and I calculate a power that the generator is producing. Okay, so that's the power being consumed from the turbine. We can also do the same thing for power delivered to the battery. The only difference in this case is that we multiply by the voltage of the battery, or the battery voltage, and instead of the open circuit voltage. So I have that plot here. Here's the power available from the turbine. Here's the power being consumed from the turbine by the generator, this blue line. And this is the power that's being delivered to the battery, this red line here. Now, I can play with the stator resistance in this case. That's the thing we wanted to find out here. If I make a stator resistance that's relatively low, say 20 ohms, we can make a generator that overpowers the turbine. And what ends up happening in this case is the wind speed will increase, the turbine will increase, and then it hits a wall where current's being supplied to, or delivered to the battery. And after that point, after these lines cross, the generator overpowers the turbine. So what happens is the turbine speeds up, gets to this point, and just stops, or doesn't speed up anymore. And the wind speed increases, and what ends up happening is the blades stall, and you don't get any more power out. So it's like the turbine hits a wall. So what I wanted to do was I wanted to make the generator weak enough so that it doesn't overpower the wind turbine. So I could increase the resistance. I suppose I put it here and get it real close. But if I had the generator like this, it's doing well. However, it might be just making the turbine sluggish. I wanted just a little bit less than that, so I just went with 32 ohms. And so this is the stator resistance that I wanted for the generator. So we know what the peak voltage is, 14 volts at 144 RPM, and the stator resistance of 32 ohms, and that's our specifications for our generator. Okay, we've got our specifications of the generator voltage and the speed at which we develop that voltage and stator resistance. Now we need some equations to convert those into design parameters. So I'm going to start with the peak generator voltage. I'll start with Faraday's law, EMF equals minus N, change in magnetic field flux, or magnetic flux, that's field times area, divided by change in time. And the maximum voltage will occur when this quantity here reaches the maximum. So that when we're changing the magnetic flux at the highest rate. So we need to know that. So what is this magnetic flux? I'm going to assume that we've got a disk. We've got round magnets, and I'm just going to model it as a constant magnetic field coming out of the disk. That would be coming up out of the paper in this case. And here's a coil wire, and it's moving across the magnet's face. And the magnet's got a width of d there, and it's moving in this direction. So we're going to get the highest rate of magnetic flux when when the magnet is at the widest point here. And so this delta BA delta T is going to be the uniform magnetic flux times this width of the diameter of the magnet times the velocity of the magnet going in the direction of these arrows. So we need to find this velocity, and I'm going to approximate it. We've got these round magnets arranged in a circle, and it's spinning, and this magnet is going to have some velocity in this direction, and that velocity is going to be omega r. So that's omega, or the speed of the generator, and then you've got the radius to the center of the magnet. And so we need to find this radius. Since we're designing this, we're going to look at different number of poles and diameters, so we need something to express this radius. And I'm modeling that as this is a circle, and it's just the circumference is the sum of all these diameters. And so we have 2 pi times the radius, that's the circumference, is equal to twice the number of poles, because each pole is going to have a north and a south, times the diameter of the magnet. And so this velocity is going to be equal to omega times this radius. The omega is going to be our speed in RPM, converted to radians per second, and then times this radius, which is our number of poles times diameter divided by pi. So there we have an expression for our velocity. So if we plug that in for our peak voltage, when the EMF is the highest, we've got number of turns, we've got 2 times number of poles of magnets. So we've got a lot of, we've got that much magnetic area that's changing. We've got the magnetic field strength times the diameter of the magnet, and this Vm that we calculated before. And so V peak is going to be 1 over 15 times the number of turns times the magnetic field times the rotational speed of our turbine times the number of poles squared times the magnetic, or the diameter of the magnets squared. So there's our voltage equation. And we have to look at stator resistance. The general expression for resistance is resistivity of the wire times its length divided by its cross-sectional area. So this is resistivity of copper. In this case, I'm going to be using copper wires, and that's about 1.72 times 10 to the minus 8 ohm meters. Okay, so the trick is to find this length, and what I did was figure I've got a serpentine coil here, and these magnets are next to each other. So this coil, for every pole, it's got to go down 1 diameter, over 1 diameter, up a diameter, and over 1 diameter, and then the pattern repeats itself. So that's for each pole. So the length is about, or for 1 turn, 1 loop is going to be 4 times the diameter times the number of poles. And then these things don't turn right away. It's like there's a kind of a dip, and sometimes there's a little bend there. And just from experience, I added a little factor of 1.2, so it's about 20% longer, just because I don't have such sharp bends. So this length is going to be 4.8 times the number of turns, because that was for 1 turn. This is 4 PD times poles times diameter. Okay, so if we plug this length into the previous resistance equation, we get 4.8 resistivity of the wire. Number of turns, poles, diameter divided by the cross-sectional area of the wire. And speaking of cross-sectional area, we've got some limitations on that. And if this is the magnet diameter, these are kind of arbitrary limitations, just what I've decided on here. So here's a cross-section area of the wire, or the coil. Here's the magnet here, and I'm saying that this coil's got to fit into a slot 30% of the diameter wide and 40% of the diameter this way. I didn't want to go wider because then it won't follow the width of the magnet quite as well, and I could put 3 of them there and make a 3-phase if I wanted to. And I just went 40% because I figured the magnetic field is starting to drop off quite a bit beyond that. So it's kind of arbitrary. You could put what you want in there. So coil area is going to be 0.12 times the diameter of the magnet squared. However, not all of this area is going to be occupied by copper. It's just round wires in a square box. So I've added a packing factor saying that we can pack about 40% full of copper. That's something just kind of based on experience. Actually, I think it could be a little bit bigger, like 0.42 or something like that. Anyhow, so we've got the number of turns times the cross-sectional area of the wire. So that's the volume of, or the area of the copper is about 0.048 times the diameter of the magnet squared. So in summary, we've got peak voltage is 1/15, NB speed in RPM, P squared, D squared. We've got an expression for the resistance. The stator resistance 4.8 times the resistivity of copper, NPD over A, the area of the wire, and then we have the space constraint, where the number of turns times the cross-sectional area of the wire has to be less than or equal to 0.048 D squared. And in this design, I'm going to assume that we're going to want to maximize the amount of copper we've got in here because that will give us the most power. So instead of having an inequality, I'm going to assume there's an equality, but we'll see that later. Okay, so we have to use those equations that we saw before for the voltage, the resistance, and the space constraints, and design a coil. So this is how I designed my coil. I took 2 of the equations here, resistance and space. If you look, this is a variable of N and A, and this also has an N term and an A term in here. So we could get a wire gauge from the A, and then we've got number of turns. And then we've got the magnet diameter and the number of poles in there. So suppose we picked a diameter of a magnet and we picked a number of poles. We specify the resistance for the stator. We can solve. We've got 2 equations. We've got 2 unknowns here. We can solve for N and A. So substituting this equation into here, solve for A and plug it in, we can calculate the number of turns. So we've got magnet diameter times the stator resistance divided by 100 times the resistivity of copper times number of poles. In the denominator here, take the square root, and we can get the number of turns. And then we can solve for A. Once we have this number of turns, we want to know what A we can have to get this specific resistance. So we put the N that we just found in here and solve for this A. And then once we get this A, it's going to be some number, but we don't have a complete set of wires that we can buy off the shelf that would have a specific A. So what we do is we pick a standard wire gauge that's close to this, either equal to or smaller. So we want it to, if we get bigger, then we're going to end up violating our space constraints. We want this to be equal to or smaller. And then what will happen is once we pick this specific wire gauge, we can go back and we can use this resistance equation and calculate the N. So we'd adjust our number of turns based on the wire gauges we can get, and then we get the right number of turns, so we make sure we meet our stator resistance requirement. So there's just a little bit of iteration there. Estimate the area, get an actual area, and then recalculate our N so that we meet our resistance requirement. And then from there we can use this voltage equation, since we have the number of turns and we've assumed a diameter. We're just working with a diameter and a number of poles. We've got our speed that we want to hit and our peak voltage. So what we can do is we can calculate what magnetic field strength we need in order to meet our voltage requirement. So the first two equations gave us number of turns and wire gauge, and this is going to tell us what we need for a magnetic field in order to meet the voltage requirement. And that will give us specifications for the magnet selection and that sort of design. This is where I determine the number of turns and the size of wire to use. Here's our volts. Now we've got our stator resistance and our speed. Those are all from our previous specifications. And in this case, I'm just picking a 1-inch diameter magnet. We can just run through the same calculations for different ones. It doesn't take a long time. So I just started picking them, and 1 inch seemed to work pretty well. So in this column, I'm just looking at different number of poles. So I just got 4 to 10. It's easy to calculate, so might as well make a whole list of them. And then I use the resistance and the space equations to solve for the number of turns. So these are the number of turns that we can fit in that space, and then the area of the wire in order to meet our resistance requirements. And then I take this area that we calculated and look at different wire gauges that have an area that's either equal to or below, and I called this one essentially equal to. And so this is the new areas based on standard wire gauges. And then I can go back, use the resistance equation to calculate a new number of turns. And then this is just a check for the resistance to make sure it's working all right. And then using the voltage equation, I can calculate the strength of the magnetic field that's required to get the voltage where we want it. And this 0.46 Tesla is pretty high. As you get to a higher number of poles, it goes down, and it turns out we can probably hit 0.14 Tesla with this particular arrangement. So I chose 8 poles, and it's going to have 26 gauge wire, 245 turns, and I just have to design my magnetics so that I get 0.14 Tesla on average through the coil. Note that I did not do anything about heat or anything like that. You might have to look at whether the coil can even carry the current, but I didn't look at that because I'm dealing with some pretty low wattages. So here's how I did the magnetic design. I have a text editor that I can change Lewis script, and this is how I can change the size of the magnet or thickness and various things. That was just to automate the process. And I used FEMM, which is a finite element magnetic simulator. I made the model as a piece of steel, and then the magnets underneath with varying polarity, and I went a magnet and a half in either direction from the center one in order to make the magnetic field somewhat uniform. And this is only a 2D simulation, so it's got its limitations, but it's better than nothing. So what I could do is I could specify the thickness of the steel, and in this case I wanted to use a circular saw, and that was 0.12 or 1.2 millimeters in thickness. So I got steel there, and this magnet here, this one is showing an N52 magnet. We can specify that, and then there would be a gap. This is the magnet here. There'd be a gap, and then the coil would start here. And so what I did is I put points on either side of the magnet, and I can just do an integral across there to find the average magnetic field at different heights or distances from the magnetic face. So then I just split it into 5, and the output is here. So each of those, as we get farther and farther from the magnet, the field strength reduces. I can just take those results, copy it, and take it over to my spreadsheet and just plunk it in here. I had already done this before, and then you can get an average magnetic field. And then what I did was I just discounted it by about 80%. That's kind of arbitrary. I just wanted to have a little bit of safety factor. So I can do that for different magnet thicknesses and come up with different Tesla ratings here. And in this case, I went with an N52. These are for N42, but I went with an N52. Gave me a little bit more magnetic field. If I discounted it, I got 0.14, and that was what we were looking for before here, this 0.14. So I figured that's probably a good magnet to pick. And that's how I selected my magnet. Okay, here's the completed coil. The leads are fed through this hole. And let's give it a resistance check. We're shooting for, let's see, is that a little bit more visible? So we're shooting for 32 ohms. Let's see what we got here. And we got 31.7, so I'd say that's pretty close. 31.8. Okay, I put a few washers in to space the magnets from the coils a little bit, try to derate it a little. So I'll give it a spin, do a single sweep. Let's see what we got here. Just a moment. Okay, the last one was about 46% too high. This is at 28 volts peak to peak, and the frequency is 18.6 hertz. So let's see, 18.6 hertz. We got 8 poles, so we divide that and then multiply by 60. So that's 140 RPM, and we've got 14 volts. So that's pretty close to what we want right there. So here's the finished generator. This is my circular saw metal plate. These are the inch diameter by 1/4 inch thick N52 magnets, and there's 8 poles, so there's 16 of these. And here's my coil, 245 turns, I believe, of 26 gauge wire, and that's pretty much it. I did space it a little bit more because it turned out my peak voltage was a little bit high, so I stuck a couple washers in there to space the magnets away and try to get the performance right where I wanted it to be. So there's the completed generator. And just a disclaimer, I don't do this professionally. I'm just showing what calculations I used, and if you try them, hopefully that will help. And if you see something that you want to change about the equations, go for it. I don't claim to be professional. Okay, 2.3 watts, 0.2 amps. Pretty good breeze. I'm guessing it's around 6 to 7 meters per second, but it's pretty variable. It'll drop off suddenly too, but we're actually seeing an increase in the total energy produced. So this thing is actually making some power.